Exactly. Okay, so we see a definition for continuity here. For all these problems, we're just going to step through continuity conditions. Now, sometimes it may be the second condition that fails. Sometimes it's the third condition that fails. Sometimes all three passes. If all three passes, then our function is continuous at that point. And sometimes we use one-sided limits, and other times we don't need to. Okay, so whenever you see like this less than or equal to, greater than or equal to, that indicates that there are different graphs on both sides of their target, which means we need to rely on one-sided limit. But a problem like this, we don't have to do that because this function is the same on both sides. Okay, this is only a point, and this is the same. So there's no need for one-sided limits. You can do it, but then you're just applying one-sided limits for the same function, which will give you the same thing.
Is this piecewise?
It's piecewise, yeah.
So you said most under like non-continuous.
It depends, right? It's possible. It's possible it's not continuous, but it's our job to discover that going through those conditions. So let's start off with number one. Okay, so even if yes. Oh, sorry, I think you're. So even if the problem doesn't specify your A value, you should be able to tell what we're working on just by looking at the restrictions, right? So here, the restriction is at 0, the restriction is at 1. So we just look at the right side to discover what we're focused on working on. Okay, so first things first, we're going to find the point. So we're going to find f of 2. Okay, what's f of 2 equal to?
0.
Right, so if I plug 2 in, it's not the first, but it's the second one, right? Because x doesn't equal to 2. We don't want to use this one for x equals 2. So f of 2 equals 5. Second condition, we want to find the limit. We want to find the limit for the graph and not the point. Okay, the point has no say as to what the limit is. It's the connected parts of the graph. This x doesn't equal to 2 means this graph exists everywhere except at 2. Okay, so all we need is one limit statement, limit as x approaches 2. And now we're just walking through our limit steps. All we've done in the past. All right, so first things first. What do we get? Yeah, 0 over 0. That means keep going. There is a value waiting for us at the end. We can factor.
Also, you can plug in 2 things like the limit. Like,
I'm sorry.
you can plug in 2 to the x. It's like the limit.
Yeah, just like the limit. Yeah, just like how we've done in the past, right? Because we are finding the limit right now. We want to know if the limit exists. Right? What's next?
X, you cancel out the x minus 2.
Mm-hmm. And limit is equal to
4.
4. So we keep going, right? We haven't failed yet. But even if option 1 fails, we keep going. But if second steps fails, then we would stop. But here we will keep going because now the third step, will it pass or fail the third step? Fail, because these are not agreeing, right? So I want you to think of the third step as something new, right? You're just looking back at what you gathered and you're just comparing it. So we don't want to say 4 doesn't equal to 5. We want to say f of 2 does not equal to the limit as x approaches 2. You could write this whole expression, or you can just call it f of x. Therefore, there's a hole in the graph. That hole is not getting filled in. That hole is living that ordered pair is living somewhere else. What type of discontinuity do we have? Removable. And we got to specify the location, right? At x equals what? 2. Yeah, that is.
So if it was not removable, that means the second one would fail.
That's right. If the second one fails, that means it's non-removable because the limit would not exist.
How's it fail? Is it like it was like undefined?
Usually the way the limit fails is if your one side limits, one side is giving you 3, the other side is giving you 7. So there's obvious disconnect.
Okay.
But here we don't do one side limit because we don't have 2 different functions. All right. Everybody good? All right, number 2.
What does the A value do again?
The A just tells you where to focus on.
Oh,
So that's basically our C value. But even if I didn't tell this to you, you would just automatically know that you're working with 0. Because 0 is the potential break in this graph. Okay. First, f of 0. Which one do we choose to plug in for f of 0? First one, because we see a line underneath this. All right, so we have an ordered pair. Second condition, does the limit exist? Can we rely on one limit statement for this? Okay, now we need 2 limit statements, right? Because we have one function coming towards 0 from the left side of 0. You got another function coming towards 0 from the other side of 0. We have to test them separately to see if they're actually meeting up or not. So the notation that we use is 0 minus, because we're coming from the left side of 0, and that is going to correspond with the x minus 4. And then separately, we got to do this 0 from the right. So we evaluate 0 in for x. What do we get?
minus 4.
Right, negative 4. 0 in for x, we get negative 4. So does limit exist? Yes, because left side is approaching negative 4. The other side is approaching negative 4. So we got to make a conclusion here. We have to say that the full limit exists. So we'll say limit as x approaches 0 of f of x is equal to 4.
The third one work too.
Good. So the third one also works. The limit exists. There's a hole there, and that hole is getting filled in by the first step. Oh, sorry. Negative 4. Yeah, negative 4. It's getting filled in, so everything lines up, right? So the third condition we can say will pass as well. So we don't want to say negative 4 to equal to negative 4. We want to actually specify what we're comparing. So f of 0 does equal to the limit as x approaches 0 of f of x. Therefore, we can say our function, continuous at x equals 0.
You have to write like continuous discontinuity.
I'm sorry?
Do you have to write the discontinuity or whatever after that? Oh no.
If it fails either the second or third one. But if it passes all 3, then our function is continuous.
Oh, so you don't need the other first
We don't need the other.
number.
Yeah. So we only are going to worry about discontinuity if we realize that there is an issue in there's a break in the graph, either a hole or an asymptote or different branches meeting up at different values. Okay, you guys want to try number 3? See if you can walk through your steps and see if practice writing out all your notations.
This one will be plugging into this middle function because it equals 1.
Exactly. Yeah. Okay, for number 3, do we need one-sided limits?
Oh, you need both sides.
Yeah, because we see a less than or greater than. Yeah, so we do need one-sided limits. Okay. What do you guys conclude here? Is the function continuous?
Yes.
Yes. Okay, all 3 conditions pass. Okay, so check your notations, see how they look. So if you do one-sided limits and they agree, make sure you rewrite your conclusion and because the goal here, the whole point of that one-sided limit is to see if you can make a conclusion about the true limit. Either they agree and a limit exists, or they don't agree and limit does not exist. So if it fails the third one, it's removable discontinuity. If it fails the second one, we would stop and say limit doesn't exist, and we would say it's a non-removable discontinuity at x equals 1. So we didn't quite see that example on this page. But hoping that we're a bit more comfortable with those conditions and how they support our conclusion about continuity and discontinuity. Okay, so I want to show you some problems on the next page. These are problems that have shown up on the AP exam in terms of how they're presented. And I think what throws students off on the next page is how to interpret an A or B as opposed to X. So I want to kind of differentiate between constants versus, or unknown constants versus variables. Okay, so if you guys can turn to the next page, I'll give you guys another moment here when any of you are finishing up. Everybody good? Okay, so next page here. Number 4, it says find the value of A and or B for which the function is continuous. And so we see later on, we're going to see when we get to derivatives, we're going to see some problems involving A and B as well. So I want to kind of just identify what the difference is between A and X. So X is a variable. Okay, that can be a moving value or a changing value. How's that? So 1 second X could be 1, another second X could be 2, right? It just depends on what it could be, right? So X is a variable that can be a changing value, but your A or B, yep, it's just some unknown constant. So the difference is that as soon as you figure out what A and B is, it's not going to change. It's not 1 second A is 3, another second A is going to be 5. So we're going to treat A the same way that we would other constants. So we'll treat A the same way if it was like a 3 or 5 or 6. It's just unknown to us right now. But once we find it, it's going to be the same unchanging value. It's unchanging value. Okay, so this feels more complicated, but the way that we're going to approach this is we're just going to walk through it, because if you look at the directions, it says find the value of A and B for which the function is continuous. So we know we're trying to force continuity out of the situation. We're trying to figure out the A value or B value so that everything lines up. So if we just simply walk through our continuity conditions, then things will appear which will allow us to solve for A without us even trying to do it. Okay, we just follow through continuity conditions. Whatever needs to happen, we're going to just make it happen, because the structure will be in place for us to solve for any variable. Okay, so we're just going to walk through each condition, and I want to show you how we can solve for A without even trying to solve for A. Okay, so first things first, our focus is at 1. That's our A value, or in this case, our C value, or focus here. So we want to find f of 1. Find the point. Which one do we use? Yep, the first one. You see the equal sign there. So 7x minus 2. Insert 1 in for x. What do we get? 5. All right, for the second condition, do we need to use one-sided limits? Yes, we have. Left side is a function, right side is a function. We want to see if they agree, and we want continuity, so we want everything to line up. So limit as x approaches 1 from the left side of 1. Limit as x approaches 1 from the right side of 1. Okay, so let's evaluate them separately. From the left side of 1, what do we get? 5. From the right side of 1, a times 1 squared, which is a. Okay, good. So in order for the limit to exist, what has to happen? Yeah, so we solve for a without even trying because we're just walking through continuity conditions. And once you solve for your variable or your constant, you can stop. You don't have to go through, continue. We're just using it.
You don't have to write the limit out, you just put a spot.
Exactly, right, because it says find the value of a or b. So here we're not trying to show the function is continuous. We want to find the a and b value so that our function is continuous. So as long as you know, okay, I got to set these equal because my one side limits have to agree, and then that will give us that whatever we're looking for, we can just solve by
Is
that.
there a chance that would ever be a problem where like a and b are up in like the same like thing or always?
Yeah, so if that's the case, then I think for now we're not going to see A and B at the same time. When we get to our next unit, we're going to see A and B. Okay, but right now we're going to this is kind of like a good introduction into some of the problems that we're going to see later on as well. But yeah, for now, I think it's just either A or just B. Okay, any questions here? Okay, so we're just using continuity conditions as our structure to help us solve the problem, to find whatever we're looking for. But then once we find it, then we can just stop. We don't have to go through the third condition because we've already reached our goal. We're just trying to figure out what A is. All right, so try number 5. Can you go through those same steps? Find your point, find your limits. See if that's enough for you to help you get to solving for A.
Even which one to start at, like plug in the 2 and 2.
F of 2. So F of 2, which one do you choose?
That one gives us less than equal.
Yeah, because the equal sign is there.
Okay. So you just say it equals like 2a or something, or like 4a.
So we want to find F of 2. So you're just plugging 2 in for X.
Okay. And you keep the variable there, the a variable.
Yeah, yeah. The A constant there, yeah. Okay, this is what I have so far. F of 2, right? We know 2 is the x value that is, oops, sorry, 6x value that we're focused on. And then we do one-side limits because, again, we have less than and greater than. We have different graphs split on either side of 2. We have to look at the limits separately. So limit is x approaching 2 from the left, I get 4a. Approaching 2 from the right, I get 4 plus a. So in order for a limit to exist, what has to happen? I got to set these equal to each other, right? So 4a equals 4 plus a. What you guys get for a? Okay. Yeah, and then once we solve for what we're looking for, then we don't have to go any further because it's not asking for us to do anything more than just solving for a. Okay. Try number 6. We can try number 7 as well. So let's go through 6 first.
Plus,
Anybody get an answer for number 6?
A equals 2.
A equals 2. Good. Okay, for number 7, we go through the same steps, point, limit, and then compare. Do we need one-side limits here? No, we don't. Okay, so the limit is just for this first statement. There's no need for us to do a one-side limits. We don't have differently defined graphs on either side of -1. It's the same graph. To the left is that x squared, is that fraction. To the right of -1 is also that fraction. It's only at -1 we have a differently defined point. Okay, so go through I'll go through number 7.
So the process is the same.
Process is the same. We only need one limit statement though. We don't need we don't need 2 one-side limits.
The limit won't be like the left side or the right side. -1 will just be like -1.
Exactly, it's just -1, right? And they'll be with the first expression. And I just want to kind of show you real quick why, if you're still wondering why we don't have to go through one-side limit, is because this goes back to number 1. Number 1 has the same structure as number 7. See that doesn't equal to 2. That means x squared minus 4 over x minus 2 is less than 2, and it's greater than 2. So I can basically, this is kind of like a shorthand way of writing this, right? So this, if you look at this and say, okay, maybe I can do one-side limit here, then that's true. One-side limit for the left of 2, one-side limit for the right of 2. But you're working with the same expression. So if you did one-side limit, you're going to end up with the same result as you would if you just did the limit one time. So there's no need to do one-side limit because you're working on the same problem and it just feels like a, feels like a redundant step. So we only need to do one side limit if you're less than and greater than are showing different expressions. But here, it's the same expression on both sides.
You get 0 over 0.
0 over 0, yeah. But then what do you do after that?
I need to factor.
You gotta factor, right? So the limit does exist, so we gotta keep going, right? Okay, so g of -1 is a. The limit as x approaches -1, we're just working with that top expression. We get 0 over 0. So we keep going, factor, reduce, reevaluate. The limit does exist. So we keep going, right? So my limit is equal to 1. So then what's my third condition?
Not equal.
Well,
equals
right, a equal 1, right? So this is an unknown constant. If I just set these equal to each other, I can solve for a. So a must be equal to 1. All right, now, if this was different, now if this was a number like 6, then yes, then we will have to say, okay, limit, we have a removable discontinuity. But here, the a is unknown to allow us to figure out what that a value must be.
So like if you're trying to look for a value, will it always be assumed as continuous?
That's right. Yeah, if you're looking, if it's looking for a value, it's always assumed that that we're trying to create continuity out of the situation. Yeah, so we're always solving for a like as if it's going to be continuous.
Is there like some scenarios where it might not be continuous?
Not with the unknown constant. There's an unknown constant. We're always working towards continuity. Yeah. Now, if that constant was known to us, if it was like 6 or 7, then the question would be, is the function continuous and can you prove that? Yeah. Okay, why don't we do a little bit of a preview into the next topic here. This is intermediate value theorem. So page 13. Okay, we did the top, right? We did the review or the warm-up problem. Okay, let's skip that continuity on closed interval. We don't have to worry about that. Intermediate value theorem. So let me read what this says. It feels a little convoluted, but I'll kind of break it down here. If f is continuous on the closed interval, so that's something that needs to be established. We have to have continuity. Okay. On the closed interval from a to b, so we're just looking at some interval. And let's say a number that we're looking for, that we're trying to target, is between our endpoints. Then there is at least one number such that that point exists. Right? So in other words, if a function is continuous, then the graph is going to touch all the y values between the two endpoints. So let's say I had this graph here. Okay. Let's say that I know one endpoint starts off at a y value 5, and the other endpoint starts off at a y value or ends at a y value of 1. And let's say I'm looking for a y value of 4.2. Is it a guarantee that this graph is going to cross 4.2 somewhere along the path? Yes, right. And that's something that you just, that you would just know just from common knowledge, right? You don't have to, don't have to worry about someone trying to teach you that information. It just makes sense that if I start off at a point above my target and then I end up at a point below my target, then there's no choice but for that target to be reached at least once, even if I don't see the graph. of course, I have to establish that the function is continuous, that there are no sudden breaks in the graph, that it's not going to suddenly jump over that value I'm targeting. But that's all intermediate value theorem is. Okay. First, establish the function is continuous. You look at your endpoints. Is one of your endpoints above your target? Is the other endpoint below your target? If it is, then I know my target is going to be reached. I think the messy thing is it's just sometimes getting into the numbers, we may kind of lose track as to what we're working with. But if we understand that concept, then this is not a difficult theorem. However, the wording and justification can be a little messy. So I'm going to walk you through that. Right? Okay, so here's example one. Use IVT. IVT is abbreviation for intermediate value theorem to show that there is a zero. So a zero is basically y equals 0. We're looking for, is the graph going to cross the x-axis on the interval from 0 to 1? Now, these are x values, okay, x values. Okay, so understand that these are x values, but we're looking for a y value of 0. So we can't say, oh, 0 is going to be reached because I start at 0, I go to 1. These are x values. This is the y value. Okay? For the function x cubed plus 2x minus 1. Okay? So the first thing is we have to establish the function is continuous. And it is because we got a polynomial. So all polynomial are continuous. There's no denominator, right? If there's a denominator variable, then we have to worry about, okay, is there a whole, is there an asymptote? But there's none of that. We can just say our function is continuous. And this is a important first step here. A lot of future theorems will require a statement about continuity. So this is a way for us to kind of practice writing out these conditions the way that we're supposed to. So it is continuous everywhere, but we're only concerned about the interval. So we're going to say our function is continuous on the interval from 0 to 1. So the next step is we want to know, are these endpoints going to produce y values above and below, right? Because we don't have the graph in front of us. We're just working on very limited information. Okay? We're seeing if we can make a conclusion about this destination based off of just very limited information from intermediate value theorem. Okay, so the next step is we got to find the y values. So we're going to take our endpoints and insert them into the function. So f of 0 is what? -1. Okay. F of 1 is 2. So maybe this graph looks like this. It may not, but I just want to kind of give you some visuals so that you're able to kind of see what's going on. So f of 0 we know is starting off at -1, so I'm going to plot that point. F of 1 is going to end up at 2. I'm not sketching the graph. I'm not using my graphing calculator, but I know my graph is going to connect from these 2 points because it's continuous. So maybe the graph looks like this. Okay. So is my graph guaranteed to cross a y value of 0? Yes, because I started at a point below and I ended at a point above. And if I have that going on, then I know it's going to have to cross through 0. Now, what if these 2 points were both positive? Then can I guarantee that the graph will hit 0?
No.
No, right. It's possible it could, but we would need more information, and we would say that IVT is inconclusive because we're just forcing ourselves to just base it off of very limited information, continuity, and the endpoints. And if it doesn't work out, then IVT doesn't apply. That's what
It passes the x-intercept basically.
it depends. Yeah, sometimes the target y value can be the x-intercept. Sometimes it could be a different y value. So we just have to look at what is the target that the problem is asking for us to find, and can we show that the endpoints, one is above and the other is below the target.
And that's it.
That's it. Yeah. Sometimes the more challenging piece is if there's a vertical asymptote. Let me see. Okay, I think I can kind of give a little bit more preview into this. So let's go to page 14. Okay, so these numbers are a little messier, but I'm just going to tell you what those values are. Otherwise, you would use a calculator, but I'll just tell you what those values are. Here it says verify that IVT applies for the function on the interval from 2.5 to 4. Again, these are x values. Keep that in mind. And then we're trying to target a y value of 6. So make sure that we're not comparing the wrong things, right? We don't want to compare x values with y values. We want to compare y values with y values.
The interval will always be x values.
That's good. Yeah, interval is always x values. And then the target is always the y value. So what I see some students do, they say, oh, 2.5 to 4. Well, 6 is not between 2.5 and 4, so therefore IVT doesn't apply. And we're not comparing the same values if we did that. So the first condition, well, the only condition is really continuity. Is this function going to be continuous everywhere?
No.
Okay. Where's the issue that we have to look at? Denominator. Okay, so there's an issue in the denominator. We don't have to worry about whether it's a hole or an asymptote. We just know that there's an issue. Where's the issue? X equals what? 1. Actually, it's a vertical asymptote. So I'm going to say that there's a vertical asymptote at x equals 1. So therefore, the function is not continuous. But do we need our entire function to be continuous for this to work? Only where?
X values of 2.5.
Yeah, exactly right. So as long as our interval is protected and there's no disruption in that interval, then we're good, right? So the only disruption is outside the interval, so we know we're safe. Okay, so we did some comparison here. We know that there's nothing that's going to intrude upon this interval, so we can say with confidence that our function is continuous on the interval from 2.5 to 4. Now, let's say there was a vertical asymptote and it did impact the interval. If I can't get past the first condition, if I can't guarantee continuity on the interval, then I would stop the problem and say, okay, IVT doesn't apply because I can't even get past that first condition. Okay, so now what's the next step? We have to find the what? Okay, use the interval to find the find the y values, right? Because we want to now determine, we want a y value above 6, and we need the other y value to be below 6. Does it matter which order they come in? No, right? As long as it could start above and end below, it could start below and end above, but we just need one. We should need both numbers to be on either side of 6. We can't have both numbers less than 6 or both numbers greater than 6. Okay, so f of 5/2, I'm just going to give you what that value is. You're just plugging that in the calculator and you get 5.8. Okay. And then f of 4 gives you 6.7. So is this going to work? Yes. Okay. I start at 5.8. I end at 6.7. So I know IVT is going to work.
You're gonna cross the line that eventually.
I'm sorry?
Yes.
Yes, because it's going to cross this 6 eventually. We don't know exactly where, but we do know it's going to cross 6. Now, the messy part is writing it out in the proper notation. So I will show that to you tomorrow. Okay. All right, you guys have homework tonight. Check your calendar. Come get your phones. Okay.
So we made this for.
That's fine. Yeah, I consider that.
Or no, not this one. Yeah. But it's there just for. And then this is one more.
Oh, yeah.
No, you should have done that. I like the call pretty much.
Favorite part of the day.
We were like hungry. Spot.